At the dawn of the 20th century, an Englishman called Arthur Evans began excavating a hill near Heraklion looking for Knossos, the legendary city of King Minos, the labyrinth, and the Minotaur. What Evans uncovered was the largest center of a Bronze Age civilization, which he dubbed Minoan, the earliest advanced civilization in Europe. In its feats of art, architecture, and engineering, Evans saw a reflection of ourselves. The Minoans observed nature closely and knew that it had a secret order, visible to those who understood its patterns. Images of plants and animals, marine life, and heavenly bodies were abundant, not only at Knossos, but all around Bronze Age Crete. The Minoans built palatial complexes whose central courtyards were aligned to the ecliptic of the sun or the revolution of the moon. Celestial objects were not only used for observation on land, but also at sea. Crete's position made it central to maritime trade routes, and the Minoans made regular trips trading goods and ideas with faraway kingdoms like the Egyptians and the Hittites. It is unlikely they would travel without celestial navigation. Their knowledge of constellations may be what is hiding behind these mysterious symbols found on gold rings. The meaning of these images is lost, but they point to a prehistoric mythology connected to the land, the sea, and the sky. It is clear that the Minoans saw the natural world as a force to be respected, but also to be used for their benefit. Their age, the Age of Bronze, marked a crucial turning point in human evolution. It took millions of years to progress from stone to metal tools, and only a few thousand years to go from metal to computer technology. Today, technological innovation moves at an ever-accelerating, often mind-boggling pace, but there is a heavy price to pay. In our efforts to improve our lives in the present, we have endangered our future. Our age, the Anthropocene, marks another turning point, where our relationship to nature must find a new balance in order for us to survive. Our oceans and climate are in measurable decline, so we are compelled to monitor environmental change. And the best way to do that is by using satellites. These satellites scan the surface of the planet in order to provide accurate information for changes in sea level. A rise of 1 single centimeter can have devastating consequences. But how can we be certain that a satellite traveling at 7 kilometers a second at about 1,000 kilometers above the Earth measures correctly and monitors reliably? This is metrology, the science of establishing the exact satellite time, its true distance from the Earth, and its exact position along its orbit, using fixed points on the ground. A professor at the University of Crete realized that the island's position made it ideal for calibration, as many satellite orbits intersected in the sky above it. Working together with the European Space Agency, Professor Mertikas and his team started developing a unique reference network of interconnected prototype devices called transponders. These devices analyze, amplify, and retransmit signals from passing satellites with high resolution and minimum bias. To achieve even greater accuracy, this groundbreaking network has now expanded to include 2 corner reflectors that safeguard transponder calibration, as well as a sea-state optical system that combines data from land cameras and satellites to determine wave height and wind speed, elements crucial to measuring the effects of climate change to weather patterns and sea currents. Their ultimate goal is to monitor the performance of satellite altimeters in the wake of quick and dramatic developments in climate and sea level change. This way, the data used for operational oceanography, weather forecasting, and ocean state and climate studies can be trusted completely, so that we can prepare precisely for what lies ahead.